Good morning, nerdlings. I'm going to look at an extension to the empirical formula problems called combustion analysis, which is really just putting an empirical formula problem into a little more of a real-world context, the way that you would actually get your data for one of these things. So first, let's recall the products of a combustion reaction. You're going to have some compound which contains carbon, hydrogen, maybe oxygen, maybe nitrogen, maybe sulfur, and you're going to combust it with oxygen gas to produce carbon dioxide, water, maybe nitrogen dioxide if you have nitrogen, and sulfur dioxide if you have sulfur. You can see that all of the carbon in the original compound ends up in one place, the carbon dioxide. All of the hydrogen ends up in the water, all of the nitrogen in the nitrogen dioxide, and all of the sulfur in the sulfur dioxide. So it's pretty easy to figure out, based on the number of moles that you have of these, how many moles of those elements you had in the original compound. The only pickle then is the oxygen, because the oxygen in these oxides can come from two places. It can come from the oxygen used in the combustion process, or it could have come from any oxygen in the unknown compound itself. So if oxygen is involved, we have a little more work for us to do, because we'll have to solve by subtraction how much of the oxygen in these comes from the combustion process, which we don't really care about, and how much comes from our unknown compound, which is what we're trying to solve for. Before we get to the math, though, a little bit on how this is actually conducted. So you would have some sealed container with a little mass of our sample to be combusted there. And then all of the gases from this are going to be collected and passed through a series of chemical reactions. The first one, they're going to come through a little chamber that's been packed with calcium salts. And that's because calcium salts plus water makes calcium hydroxide plus removing a hydrogen ion. So let's balance this guy out. There we go. Now we're all balanced. So after this, we've removed all of the water from the exhaust stream, so that's gone. And you could figure out, if you knew the weight of these salts before and the weight of them after, any additional weight is the amount of water that's been released by your exhaust gases. After that point, our exhaust gas, switch back to black. Our exhaust gases are what we would call dried, because they've been removed of any water in them. And next, they're going to be bubbled through a big tank of actually the same chemical that we just made here, calcium hydroxide. And that's because in this tank, the calcium hydroxide will absorb any carbon dioxide that we have to make calcium carbonate and water. And we know from our solubility rules that calcium carbonate is a solid. So we bubble bloop, 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 our carbon dioxide through this solution, and it reacts with the calcium hydroxide, and it starts to make a precipitate of calcium carbonate, which is going to collect. We can then filter and weigh that. And now we've removed yet another thing from the waste stream, and you can find the mass of the calcium carbonate, and you can see from the stoichiometry here that for every 1 mole of calcium carbonate you have, that was 1 mole of carbon dioxide that was in your waste stream. There are other similar reactions where the gases will then be passed through to scrub off the nitrogen dioxide and the sulfur dioxide. I don't really need you guys to know about those. The only two that I need you to be aware of are calcium salts plus water makes calcium hydroxide. I just wrote the net ionic equation here, so this could be any soluble calcium salt, so it could be calcium chloride or calcium nitrate. They all work and will produce calcium hydroxide. And then whatever the counter ion here would be associated with the hydrogen cations in solution. And that calcium hydroxide plus CO2 makes calcium carbonate plus water. Okay, so that's a little bit about how this is actually done. Let's get on to the math. Our strategy is to use the masses of our oxides to find the moles of carbon, hydrogen, nitrogen, and oxide. And that's because if we have 1 mole of this, there would have been 1 mole of carbon present. If I have 1 mole of water, that's actually 2 moles of hydrogen that were present and are unknown because there were 2. For every 1 mole of this, that's 1 mole of that. And 1 mole of this is 1 mole of that. So we've figured out, based on the mass of the oxides produced, how many moles of these there were in our unknown compound. Anything else, most likely going to be oxygen, we're going to have to solve for by subtraction, and we'll see some examples of that. And at that point, you will have moles of all the things in your compound, and you can solve it just like an empirical formula problem, where you normalize using the lowest number of moles. Okay, let's start with an easy example here. So, what we know is we've put in a 15-gram sample. It contains only carbon and hydrogen, so I don't have to worry about oxygen, nitrogen, or sulfur. So this is a fairly simple one, just those 2 things. And the 15 grams produced so many grams of carbon dioxide and so many grams of water. So I'm going to write out what I know. I have, switch over to the pen. I have 15 grams of something, and it has made 43.91 grams CO2 and 26.96 grams of water. So at this point, we're going to, like an empirical formula problem, we're going to convert these into moles. Some molar masses that you'll see me using a lot because we're always dealing with carbon dioxide and water. So molar mass of carbon dioxide, 44.009. And so that gets me 0.9978 moles of CO2 and 18.015 is the molar mass I'm going to be using for water, and that gets me 1.497 moles. So again, kind of like an empirical formula problem, I'm going to be pretty careful with my sig figs because I could run into rounding issues like you saw in the previous video. So I've got 4 sig figs, so I'm going to use 4 sig figs in my process. Alright, so at this point, this means if I have 0.9978 moles of CO2, that means I have 0.9978 moles of carbon because there's 1 carbon in the CO2. My hydrogen, on the other hand, there are 2 hydrogens in every mole of water, so I'm going to multiply this by 2, and that tells me that I have 2.993 moles hydrogen. Okay, so now we're just going to treat this just like an empirical formula problem, normalize by the smallest number of moles, which is this guy. So divide out by 0.9978. Naturally, that's 1. And divide out by 0.9978. And this is really, really close to 3 with 4 sig figs. So we have an empirical formula. My final answer would be CH3, and that's my empirical formula. Done and done. Let's look at one that's a little trickier. So this one's a little bit trickier because we have carbon, hydrogen, and oxygen. So I've got a 12-gram sample with 3 elements in it. It produces this many grams of carbon dioxide and this many grams of water. So this is one of the ones, like I said, where we will have to solve by subtraction for this oxygen, because we don't know the oxygen that is in these. Some of it comes from our unknown compound, some of it comes from the oxygen used in the combustion process. So let's write out what I know. So I have 12 grams of something containing carbon, hydrogen, and oxygen. Produces 17.20 grams CO2 plus 9.39 grams water. Okay, same process. Divide by those molar masses. You'll be getting really familiar with these. 44.009 for carbon dioxide, so that gets me 0.3908 moles, and 18.015 for water, and that gets me 0.521 moles. Okay. This is equal to my number of moles of carbon, again because there's one carbon in this, and multiply this guy by 2, to get my moles of hydrogen. So right now, if the compound contained only carbon and hydrogen, we'd be ready to normalize because I have the moles of both of those. But there's another thing in there. So now it's time to solve by subtraction for how much oxygen is in there. The strategy I'm going to use is, if I had 12 grams of this, I can figure out how many grams are from the carbon, how many grams are from the hydrogen, and then the balance of that is going to be the mass that comes from oxygen. So I'm going to take my moles of carbon, and I want to multiply that by the molar mass of carbon, and I'm going to add that to my moles of hydrogen times the molar mass of hydrogen. Add all of that up, and I get 5.74 grams. So 5.74 grams of this comes from carbon plus hydrogen. So that means the remainder is my oxygen. 12.000 minus 5.74 gets me 6.26 grams oxygen. And so now, almost there, I can convert this to moles of oxygen. And now I'll be ready to normalize and get my answer. Before we do that, let's recollect what we did. Mass of carbon dioxide divided by molar mass of carbon dioxide gets me moles of carbon dioxide, which is the same as my moles of carbon, 1 to 1. Mass of water divided by the molar mass of water gets me moles of water, double that to get my moles of hydrogen. At this point, I'm going to convert these numbers back into masses, So moles of carbon times the molar mass of carbon, moles of hydrogen times the molar mass of hydrogen. Add that together to find how much of my 12 grams comes from carbon and hydrogen. So I've got 5.74 grams is coming from carbon and hydrogen. So the rest must be the oxygen. So now I subtract mass of the total compound minus the mass of the carbon and hydrogen that I just figured out, gets me mass of oxygen. Convert back to moles. And at this point, I have moles of my three things involved. I would be ready to normalize. So I'm going to scoot this up just a little bit so I have some room to write. So 0.39, that's a really sloppy 9, 3908 moles C, 1.04 mole H, and 0.391 mole oxygen. Normalize 8.3908. Okay, and so this one is going to be really, really close to 1. And this one gets me 2.66, and this one gets me 1 again. Okay, so like an empirical formula problem, this guy can't round him off. These are really close to whole numbers. This one we're going to have to think about what fraction that is. I recognize this as sort of the decimal equivalent to 2/3. So I'm going to turn this number, into 8/3. And so this is 3/3 and 3/3. And now I can multiply those all out by 3. So my empirical formula is C3H8O3. And there's our process. So just to recap, divide by molar masses to get moles of carbon and hydrogen. Make sure you double the hydrogen because there's 2 hydrogens in water. Even though we just turned masses into moles, now we're going to go back again to turn moles into masses of carbon and hydrogen. Get the sum of the compound that's carbon and hydrogen. The difference is the oxygen. Convert the oxygen mass into moles of oxygen. Normalize just like a regular empirical formula problem. Whew. Oh, it gets worse. Not much worse, but nonetheless, now we have 4 things involved, and we produce so many grams of carbon dioxide, so many grams of water, and here's our new guy, so many grams of nitrogen. So let's write what I know. I put 6 grams in, I get 10.88 grams carbon dioxide, 2.783 grams water, and 5.686 grams NO2. Same process now, divide out by molar masses. 44.009 gets me 0.2472. 18.015 gets me 0.1545. And the molar mass that I'm going to be using for NO2 is 46.005. And so that gets me 0.1236 moles. Okay. This is 1-to-1 with carbon, so this is my moles carbon. Double this guy to get my moles of hydrogen. And this is 1-to-1 with moles of nitrogen, so this is also my moles nitrogen. Again, like before, on the last problem, I have everything except for one. I have my moles of carbon, I have my moles of hydrogen, and I have my moles of nitrogen. And so, like before, I'm going to take these moles, turn them back into the masses of their elements, and figure out how much of this 6 grams comes from carbon, hydrogen, and nitrogen, and the rest is going to be coming from oxygen. So 0.2472 times 12.011 for my carbon plus 0.3090 times molar mass hydrogen plus 0.1236 times molar mass of nitrogen. Add all of that up, and I get 5.012 grams coming from carbon, hydrogen, and nitrogen. So that means 6 minus 5.012 gets me 0.988 grams oxygen, which is 0.0618 moles of oxygen. So now I'm ready to normalize because I have moles of carbon, moles of hydrogen, moles of nitrogen, and moles of oxygen. So 0.2472 mole carbon, 0.3090 mole hydrogen, try and get me enough room to write my nitrogen along the same line. So there we go. This is my smallest guy, so I'm going to divide out by 0.0618. And what we get is 4, pretty much with sig figs. 5, again, pretty much even with it on sig figs. 1 and 2 with sig figs. So my empirical formula, you don't need to convert to fractions or anything. We've got all whole numbers. C4H5 And we are done. So there's that whole process again. Convert masses to moles, double to get moles of hydrogen, turn those back into masses of the elements so that you can solve for mass of oxygen by subtraction, convert that to moles, normalize, finished. Okay. Sometimes you will get a problem where there will be an element that isn't really involved in the combustion. And that can make the problem appear in a little different ways, maybe. In this case, it doesn't, and you'll see why. Because if we have a compound containing C, H, and Cl, there's only one thing that I don't have information about, and it's the Cl, because all my carbon is here, and all my hydrogen is here. So basically, this is going to be treated just like oxygen in the previous two examples, where we get the masses of carbon and hydrogen, and then can subtract out to get my mass of chlorine. So, let's go for it. 10 grams of the thing that contains carbon, hydrogen, and chlorine makes 5.182 grams of CO2 and 2.121 grams of H2O. I'm just completely not going to worry about what happened to the chlorine in the combustion. That's not a standard product for a combustion, so don't try and do anything chemically with it. We'll just solve for it by subtraction because we don't really have to worry about whatever it did in the combustion process. So here's our usual molar mass suspects. .1177 moles carbon, 0.1177 again moles of water. Multiply that by 2 to get my hydrogen, so 0.2354 moles hydrogen. Okay, like I said, this one is not going to cause any differences because we've got 2 of the 3 things. Now we can solve by subtraction just like we did before. 0.1177 times 12.001 for my carbon plus 0.2354 times 1.008 for my hydrogen, and that gets me, of the 10 grams, 1.651 grams are carbon and hydrogen. So the balance is my chlorine. Convert chlorine to molar mass, or to moles. Divide out by 35.453 is what I'm going to use for chlorine. And so now I have the moles of all 3 things, and we can normalize. Divide by the smallest. We get 1, 2 for all intents and purposes, and 2. So my empirical formula for this CH2Cl2. So nothing really any different than the last two problems. Just don't get confused by the Cl or try and predict a product for it. That's okay. As long as there's just one guy that you don't know, then it's the one that you're going to solve for by subtraction. And there's the key step in all of the solve for subtractions. Get the moles of 2 of them, or get the moles of all but 1, I should say. Sum them up to get their masses, and then the difference is the mass of the one that you don't know. Last example here, and probably about as tricky as you might see them. This one is especially diabolical because we have 4 things: carbon, hydrogen, oxygen, and chlorine. So here's a guy again. I don't really know what happens to chlorine in combustion, and so it's going to be a bit of a mystery. But I also have to solve the oxygen by substitution. So now there's 2 things in here that I don't know, and I can't handle that without a little additional information. And because people who write questions are usually problematic, they're going to give that to you in about the most obscure, obfuscated way possible, and tell you that some additional test was done, and in some shape or form they're giving you percent composition of whatever the oddball element is. They could be really nice and just tell you the percent composition is blah, but probably not. They'll probably make you work it out for yourself. So this is the extra information that is new. So let's go ahead and work that out. So if this many grams of a 5-gram sample is chlorine, I can work out that chlorine is 43.50% of the unknown. And because they were being difficult and giving us the percent of chlorine using a mass that isn't the same as this, I can now go and take this and figure out what mass of this sample, the 15-gram sample that tells me about carbon and hydrogen, is chlorine. And so 15 grams times my 43.5% tells me that I have 6.525 grams chlorine. At this point, this is the only really extra stuff that there was. It's going to proceed like normal now, so I'm going to zoom out, get me a little extra room here, and go from there. So I have 15 grams of my thing that has carbon, hydrogen, oxygen, and chlorine, and it has made 24.299 grams CO2 plus 3.316 grams H2O plus 6.525 grams of chlorine. And so I got that number by the percentage. So figured out the percentage using this, and then if I'm going to be using the 15-gram sample to get my carbon and hydrogen, I'm just going to go ahead and figure out, what is 43.5% of this. That way I can have all of my data in one problem. So I've got the number that I'm going to use to figure, switch back to the laser pointer. Number I'm going to use to figure out my carbon, number I'm going to use to figure out my hydrogen, and then just chlorine. And I'm not going to get fancy and make it Cl2. I don't really know that. I just know that of this 15 grams, 6.525 grams are chlorine. Okay, proceed like normal. Molar masses, that should be a 44. So 0.5521 moles carbon dioxide, 0.1841 water, and so that means 0.3681 mole hydrogen. Divide out by 35.453. That's what that's supposed to say, molar mass of chlorine. And that gets me 0.1840 mole chlorine. Okay, now solve the oxygen by substitution. So 0.5521 times carbon's molar mass plus 0.3681 times hydrogen's molar mass. You can, if you want to, take this and multiply it back by its molar mass to get mass of chlorine, or you can just recognize that you already know that, plus 6.525 grams of chlorine. And so all of that adds together to make 13.53 grams carbon, hydrogen, and chlorine. And so 15 minus 13.53 gets me 1.47 gram oxygen. Which is 0.092 moles of oxygen. Okay, and we're almost home because we've got moles of all of our substances, all of our elements. Time to normalize and call it a day. 0.5521 carbon, 0.3681 hydrogen, and 0.1840 chlorine. Divide out by the smallest, which is my oxygen moles, so dividing out by 0.092. And I get essentially 6, 4, 1, and 2. So empirical formula, C6H4O Cl2. Okay, so the extra bit for this last problem was here, and we had to conduct this because there were two things that we didn't know about from our combustion products. We were uncertain about the oxygen and the chlorine. Additional information was given that allows us to get percent of chlorine. If the question writer is nice, they'll just give you the percent of chlorine. If they're not nice, they'll give you some additional information that allows you to get the percent of chlorine. Using that percentage, you need to figure out how much of the sample was chlorine. And at that point, that's as good as any of the masses of a combustion product. So once you're there, then it works just like the other ones. Divide by the molar masses to get moles, and solve for anything that you need by subtraction. And so in this case, we had the mass of chlorine. Again, if you wanted to run this again to make it look like, moles times molar mass of carbon, moles times molar mass of hydrogen, I could have done 0.1840 times 35.453 to make it look the same, but that's just going to get me my 6.525 number back. Whatever floats your boat, that saved me a little step there, and that gets me mass of carbon, hydrogen, chlorine. Solve for oxygen by subtraction, normalize like normal. And that is combustion analysis. Long problems. So, hope this helps. Hope you guys are successful with the problem set, and we will talk to you later.